Welcome back, everybody. This is a continuation of our Chapter 5 notes on Newton's laws and forces. And I'm going to introduce a new kind of, not a new kind, but a new name for a force to you today. And that's the idea of what's called the normal force. Now, before you get any ideas, the normal force doesn't imply that other forces are abnormal. What normal means is, well, it can have a couple different meanings, but in this scenario, in this case, normal means perpendicular. If you are normal to something, you might say you are looking at it directly. All right, you're not looking at it at an angle. All right, you're looking directly at it at a right angle. So perpendicular, you might say these lines right here are not normal, but these lines right here are. You might say this line is normal to this. All right, so we're talking about a sense of being perpendicular. Go ahead and delete them. All right. So, well, what does perpendicular matter? Well, perpendicular matters when we're talking about a surface supporting another object. Let's say right here I've got a tabletop, okay, and I've got an orange box on top of it, right here, like so. And that orange box has mass, and this is assumed to be on Earth, and so it's going to experience Earth's gravity. And so mg is the weight force that is being directed downwards of gravity acting on this box. All right. Well, why does the box not actually move downwards? There's a force applied to it. Why does it not move? Well, you can say, all right, well, it's resting on the table. It is, but more accurately, we should say that the table is applying a force to keep that box in place. Now, a table doesn't randomly apply forces, but this force that we call the normal force, sometimes people call it F sub n because they don't like the fact that n is also the symbol for Newton as well, but I use a capital N. The normal force is, first of all, at right angles to the surface, and it is a force that the surface has to apply in order to prevent the box from crashing through the table. We say right here that it's caused by the electromagnetic force. Oh, what does that mean? Well, there's an electromagnetic force that is holding atoms together, and your table is made of atoms that are linked together, and when you have a downward weight force applied to a table, you're actually stressing the forces between those atoms such that they have to, such that there is, you might say, a cumulative force applied to resist that downward weight force. Let's say you had a really, really weak table. The box would crash right through it because the atoms can't hold together. But most tables are designed to be strong, and so they can resist this downward weight force, and so the table has to apply an upward, what we call normal force, to support the box. All right. We'll talk about supporting forces a little bit later, but it's basically the same thing as a normal force. All right, but normal means that there's a force that you might say the force that a surface applies is always going to be at right angles to that surface. So here's the surface. The surface is applying it directly up at right angles to it, so we call that the normal force. All right. So in this case right here, the normal force is going to have to be exactly equal but opposite to the weight force, right? We're going to find in other scenarios that's not always the case. But when an object is at rest, there's no acceleration, the normal force acting up is going to be equal yet opposite to the downward force of weight. So, with that being said, let's look at our first scenario, or our example for this video segment, and we're going to be seeing how acceleration and normal forces kind of work together. All right. So we have kind of an opposite tug of war. You might call it a push of war. You've got two boys that are pushing on an ice block right here. Okay. So this ice block, first of all, we use ice because whenever we don't want to have to deal with friction, we just pretend that ice is frictionless. It's not, but it mostly is. All right, so in this problem, you don't need to worry about friction. You've got this boy applying force 1 at a pretty high angle, 60 degrees, to the ice block. And it's directed sort of towards the other boy, but very much down. And this boy right here is applying a force, force 2. By the way, those are 13 newtons and 11 newtons, respectively. A force 2, kind of in the opposing direction, but at 30-degree angle from the horizontal. And we want to find two things. First of all, we want to find the acceleration of the ice block. All right? And secondly, we want to find the normal force the table is going to be exerting on the ice block. All right? The table has to support all this nonsense going on up here. These boys pushing back and forth and down, and also the weight of the ice block as well. So how much force does the table actually have to apply upwards? That's what we're going to find out. Okay? So let's take, and I'm going to take this and simply shrink this down a little bit so I can I'll put it over here. All right, and I'm going to redraw my ice block. Here's my ice block right here, and the table that is supporting it, I'm going to draw right underneath it like that. All right, it's got a couple different forces acting on it, doesn't it? It's got this really high force 1, and that is 60 degrees from the horizontal. All right, and force 2 is a little more shallow. Force 2, and that is, hopefully I can fit it in there, 30 degrees above the horizontal. Like so. Not only that, but we've got one more force that the block itself is creating, and that is a result of its mass being accelerated by gravity, so that's mg right there. Okay? So, let's do part A. Let's find the acceleration of the ice block. Now, one thing we're assuming right here is that the table is supporting the ice block the whole way. The table is not breaking. It's not going to crash or lose a leg or crumble, and so there's going to be no motion of the block in the y direction. When we say find the acceleration, we're finding which way it's going to accelerate left to right, or along the x-axis. All right, so the acceleration on the x-axis is what we want to find out. Okay, well, we're going to need to sum the forces then in the x direction. All right. Net force. In fact, one thing we can do right off the bat is make a statement about the net force in the x direction, right? That equals mass of the block times acceleration in that x direction, right? You know, I shouldn't put that b there. I'm just going to put m. It is the mass of the block. It's the only mass we're dealing with right here, but I'm going to keep everything just x subscripts right there. The other way we can make a statement about the net force is about the forces that are in that direction. Well, we don't have the forces in the x direction. We've got two forces at angles, two different angles, 60 degrees and 30 degrees. So we need to take them and turn them into x and y components. So let's just go ahead and do that right now. All right, so force 1 equals, what is force 1? 13 newtons. 13 newtons at 60 degrees. What direction is that? That's applied south of east, right? South of east. And I'm going to move down here and save some space a little bit. Force 2 equals 11 newtons. I should say make some space. At 30 degrees south of west, right? Because that's what direction that is right there. Okay, why did I leave those spaces in there? Well, that's because we're going to be writing in our x and our y components of those forces. F1x is what? How do we get the x component of something, of a vector? Magnitude times the cosine of theta, right? So 13 cosine of 60 degrees. What do we get? 13 cosine 60. I get 6.5. 6.5 newtons. Now, before we go any further, let's ask ourselves, this x component right here, is that positive or negative? It's positive, right? So we can leave that as is. But let's do the y component. F1y, that's going to be 13 sine of theta, right? 13 times the sine of that angle. So 13 sine of theta, I get 11.3, we'll say. 11.3 newtons. Is that positive or negative? It's being directed downwards, isn't it? So that F1y is going to be negative, so we've got to put a negative sign in front of that 11.3 newtons. All right, let's do the x and the y for force 2. Force 2x, that's going to be 11 cosine 30, right? I get 9.5. You know what? I left an extra decimal. I'll just say 9.53. 9.53 newtons. Now, is that going to be positive or negative? I should make a little more space here because it's going to be negative, right? It's acting in the negative x direction. So we're going to put a negative sign in front of it. And how about the y direction? The y direction we're going to find also is negative, right? So F2y, F2 in the y direction is going to be 11 sine of 30. So that is 5.5. 5.5 newtons, but it's, I didn't leave enough space for the negative sign. It's negative 5.5 newtons, right? Because it's acting downwards. Negative 5.5 newtons. I'll just leave that with two significant figures for now. Okay, so let's sum the forces in the x direction, because the acceleration in the x is what we want to find. Okay, I'm going to go back up here and in this little spot right here, make a statement about the net force in the x direction. I guess it might be more helpful if I had written that in green, because green is typically our x direction, but that's all right. In the x direction, we've got a positive x, 6.5 newtons, and we've got a negative x, right? So, I'm going to do 6. I will write them in green. 6.5. I'm going to call the positive direction, and the opposite direction I'm going to call negative, so it's going to be minus 9.53 newtons. Okay? It's in the opposite direction. All right. Mass times acceleration equals these two forces added up together right here. We should be able to solve for the acceleration right now. Both of these statements about the net force are equal to each other. So I'm going to come down below. I'm going to write this in black. We can say mass times acceleration in the x direction is going to be equal to 6.5 minus 9.5 newtons. So therefore the acceleration in the x direction is going to be 6.5 minus 9.5 divided by the mass of that block of ice. What is the mass of the block of ice? 6 kilograms, right? 6 kilograms right there. 6.0. This will give us our acceleration of the block. And I think we're going to find that the boy who's applying less force is actually going to be winning. All right? And it's all going to be because of his angle. So 6.5 minus 9.5, that's minus 3, right? Minus 3 divided by 6, so that's going to come out to negative 2.0. Oh, no, sorry, negative. I'm trying to do that in my head. Negative 0.5, right? Negative 0.5 meters per second squared. So the negative direction is going this way. So the boy that's pushing with less force, only 11 newtons, is actually going to win. Because he's applying his force more in the x direction than this boy is right here. Okay? All right. Let's see if I can, what I might just need to do is, I'm going to stop for now. I'm going to stop this at part A, and I'm going to finish part B in a separate video. It'll be hopefully significantly shorter, But I don't want to make this one any longer, so we'll stop at the end of part A and pick up with part B on the very next one. Thanks for following along. See you on the next one.